So today, we're going to dive into a concept that's really one of the biggest deals in artificial intelligence, something that's quietly running the show in so much of your digital life. We're talking about supervised learning. It's a core engine of modern AI, and we're about to break down exactly how it all works.
I mean, think about it. Have you ever wondered how your email inbox is so good at catching junk mail? Or how your favorite streaming service just knows what you're going to want to watch next? Well, the answer to that, more often than not, is supervised learning. It's the secret sauce making our tech feel so smart.
So, what even is it? Honestly, the best way to think about it is like teaching a computer with flashcards. You show it a picture, that's your data, and you tell it, this is a cat. That's the label. You do this thousands, maybe millions of times, and eventually the machine starts to see the patterns all on its own. It's learning, because we're supervising it with all the right answers.
All right, so here's the game plan for this explainer. First, we'll walk through the basic recipe for how it's done. Then we'll get into the two main kinds of problems it can solve. After that, we'll do a quick tour of the most important algorithms, see where this stuff is popping up in the real world, and wrap up with the big challenges ahead.
Okay, first up, let's pull back the curtain on how this stuff actually works. Pretty much every supervised learning project out there, whether it's for predicting stock prices or spotting diseases, follows the same fundamental blueprint.
So, it all starts with gathering those labeled flashcards. Then, and this is super important, you have to clean that data up, because real-world data is almost always a mess. After that, you split your data. You use the biggest chunk to train your model, but you keep a small, precious bit aside for testing later. Then the fun begins. The model learns from all that training data. Once it's trained, you test it on the data it's never seen before to see how well it does. If it passes the test, boom, it's ready to go out into the world and make predictions on brand new stuff.
Okay, so we've got the how. Now let's talk about the what. What kinds of problems can we actually solve with this? Well, it mostly boils down to two core jobs: predicting numbers and predicting names or labels. And that simple difference covers a huge range of what AI can do.
On one side, you've got what's called regression. This is all about predicting a number on a spectrum. The questions it answers are things like, how much or how many? On the other side, there's classification. This is about putting something into a bucket, giving it a name. The questions here are, which one is it? Or is this an A or is it a B?
Let's make that a little more real. Regression is the magic behind predicting a house's price based on things like its size and location. It's what companies use to forecast their sales, what your weather app uses to estimate tomorrow's temperature, and what Wall Street uses to try and guess where a stock is headed.
And here's classification in action. Remember that spam filter? Classic classification. Your bank flagging a weird charge as fraud or genuine? That's classification too. In healthcare, it can help decide if a scan shows disease or no disease. And of course, it's what lets your phone look at a picture and say, yep, that's a cat.
All right, now for the fun part. Let's meet the actual learners, the algorithms. These are basically the different strategies the machine uses to figure things out from the data. We're just going to take a quick tour of a few of the biggest names in the toolkit. First up, we have the old faithful, the workhorse, linear regression. This is for our predicting numbers tasks. All it's trying to do is find the single best straight line that cuts through all the data points. That's it. It's super simple, incredibly fast, and it's a great place to start when you think the relationship between your data is pretty straightforward.
So yeah, it's perfect for things like sales forecasting or salary estimates. But its biggest strength is also its biggest weakness. It just can't handle complex, curvy relationships in data. And if you have a few really wild data points, what we call outliers, they can totally throw off its prediction. So you're trading complexity for pure speed.
Next up is the decision tree. Now this one is super intuitive. It works by asking a series of simple if-then questions that split the data up. Seriously, it's just like playing a game of 20 questions. Is it bigger than a shoebox? Yes. Does it have fur? No. Each answer sends you down a different path until you land on a final prediction.
What's great about decision trees is that you can actually see their logic. They make sense, but they have this one huge flaw. They can start to overthink the data. This is a problem we call overfitting. It's where the model basically memorizes the training data, noise and all, so perfectly that it totally fails when it sees something new.
So just picture this one lonely little tree. It tries so hard to be perfect on the training data that it builds this crazy, complicated mess of rules. And that makes it really fragile. If you change the data just a tiny bit, you could get a completely different tree. It's just not stable.
So what's the solution? Well, what if instead of trusting one fragile tree, you built a whole forest of them? This is the brilliant idea behind something called a random forest. You build hundreds of slightly different trees and then just let them vote. It's like the wisdom of the crowd. All the individual mistakes cancel each other out, and you end up with a way stronger, way more accurate prediction.
Okay, last one for our tour, K-nearest neighbors, or KNN. This might be the simplest idea in all of machine learning. To figure out what a new thing is, it just looks at its closest neighbors and sees what they are. If you tell it to look at its 5 nearest neighbors, and 3 of them are dogs and 2 are cats, KNN is going to say, well, it's probably a dog. The whole idea is just, you are the company you keep.
This simple logic makes it amazing for things like recommendation engines. You know, if you like these 5 movies and your neighbors also liked them, you'll probably like this other movie they watched. But here's the catch. To make just one prediction, it has to compare the new data point to every other point in the whole data set. So if you have millions of data points, it can get really, really slow.
So we've been in the weeds a little bit with the algorithms and the theory. Let's zoom way back out. Why does any of this actually matter to you? Because this stuff isn't just in a research lab anymore. It's completely woven into the fabric of our world. I mean, supervised learning is helping doctors spot diseases in medical scans. It's what your bank is using right now to stop credit card fraud. It's the engine behind all those product recommendations you see when you're shopping online, and the reason you see certain ads. It's even on the front lines of cybersecurity, sniffing out new threats. It is truly everywhere.
But, and this is important, it's not magic. For all of its incredible power, supervised learning has some major hurdles that people are trying to solve every single day.
The biggest one is probably the need for all that labeled data. Remember our flashcards? Well, getting actual people to accurately label millions of data points is incredibly expensive and takes forever. We've already talked about overfitting, that constant fight to make sure the model is learning a real pattern, not just memorizing. And then you have weird issues like imbalanced data. In fraud detection, for instance, 99.9% of your data is not fraud. That makes it really hard for a model to learn what the rare cases of actual fraud look like.
And all of this leads us to a really crucial final thought. We are supervising these machines. We're teaching them based on the data we give them. They can only be as smart as the examples we provide. So what happens if our data is biased? What happens if it has its own blind spots and doesn't fully represent the real world? At the end of the day, a model is only as good and as fair as the data it learns from. And that is the biggest challenge of all as we keep building our future with these amazing tools.